Hello everyone, and thank you for joining me. In this video playlist, I'd like to talk about enterprise internet connectivity. To do this, I had to change things up a bit. Because up until now, we've been talking about interior gateway protocols and analyzing the intrinsicies of the various IGPs that could be deployed in your enterprise environment today. However, if you have an IGP already set up, then you most likely already have internet connectivity, because you're going to need a way for your enterprise users to route through your autonomous system and reach other autonomous systems out on the internet. So what I did is I created this topology so that we can go over the different internet connectivity models and interconnectivity types. The simplest of all internet connectivity models is the single homed environment, where you have one link to one ISP. This model, however, is the most vulnerable because there are two fault scenarios that could exist. Either the link could go down, or your ISP router could have some issues. In this particular type of scenario, if any one of these faults actually occur, you've completely isolated your enterprise environment from actually reaching the internet. So, the single homed interconnectivity model is the most vulnerable because it has the highest level of fault probability. There is no resiliency at all in the event of a failure. We could move to the dual homed environment, which is two links to one ISP. So essentially we double up on these internet links here. Okay, we could do that. And even though we do, to a certain extent, resolve or provide resiliency at a link level, there is no ISP resiliency in this model. We have a single point of failure due to the ISP going down. Now, the most ideal situation, at a minimum, would be the single multi-homed environment, where you would be connected to two different ISP providers. So one link to two different ISP providers. This provides internet redundancy and solves a lot of the problems that are present with the single or dual homed environment. However, the best resiliency or redundancy model by far is the dual homed environment, which is two pairs of independent links going to two different ISP providers. This provides the most redundancy by far. But for the sake of this video series, we're going to start off with a single homed model and work our way to a single multi-homed model. And then at that point, you can just double up the links, but because the principles will still apply. So moving along, we have a single homed model currently right now. And in this single homed model, we have a point-to-point link, and I could basically create a default route pointing to the next hop interface of this ISP, and it would work perfectly fine under this single homed environment. However, we've adapted the strategy of implementing an eBGP neighborship. We want to create an eBGP neighborship, and the reason is because we're planning for further expansion and have decided to be a little bit proactive. So let's talk a little bit about BGP. So eBGP is an external border gateway protocol, which is essentially a protocol that all autonomous systems out on the internet use to exchange full routing tables. Now, BGP is a path vector protocol that uses policy-based routing techniques and provides inter-domain routing between autonomous systems. Now, to accomplish this task of a neighborship between these two routers, I would like to review my configuration with you. Okay, so first off, we need to create a point-to-point link. I've used the IP address of 200.1.1.0/30 as the subnet of this point-to-point link. The second phase is we'd have to go under the config T of the router and turn on the BGP process, which is router BGP, and the autonomous system that Acme Edge 1 pertains to, which in this case would be 34.987. Once we've done that, we can move to the neighbor command, because you statically define your neighbors in eBGP. So we have to statically define our neighbor with the IP address, which is going to be established on the actual physical IP. So you can see how the ISP has .1 and Acme Edge 1 is .2. So neighbor .1 has to be also with this criteria of pertaining to the AS, the remote AS of 1587. Now the same thing happens on the ISP side, all right? Okay, that also happens on the ISP side. What's also important is that we are going to announce the default route via eBGP. So instead of actually creating the static and pointing to the next hop interface, we're going to use an eBGP relationship where the ISP is going to announce the default route with the default originate command, right? But the most important thing is that when you're creating an eBGP relationship, there are two network administrators, one on the ISP side and one on Acme Edge, that have to work together and collaborate to make this neighborship possible. You can't do it all on your own, okay? So that's another key point that needs to be understood. Now, this will create the neighborship, but it's not enough, okay? This will allow the eBGP process to come up and a neighborship to be established, but it's not enough. And the reason is because we need to announce out IP addresses to the internet. And to do that, we use the network command, all right? The network command is important because it forces BGP to inject routes it has in its routing table, meaning you can only announce prefixes that sit inside your routing table. If these prefixes didn't exist within the routing table, you wouldn't be able to announce them to the ISP. Now, what does that mean? What that means is that if you take a look at these prefixes here that are located in the access layer, they're able to be announced out to the ISP because they find their way into the routing table of Acme Edge 1. And they do that via the IGP. See, the internal gateway protocol is used to allow these prefixes to properly flow up to Acme Edge 1. As soon as Acme Edge 1 has these prefixes in its routing table, these prefixes are now eligible to be announced out in the eBGP update to the ISP. If these prefixes do not make their way into the routing table, they will not be announced out. So it's very important that these prefixes never go down. And there are tactics and techniques that are used to make sure that these prefixes never get lost in the routing table of your edge router. And we'll go over that, okay? Now, there are a couple of things that I'd just like to talk about when it comes to BGP. Some generic information that I think is very important. So number one, when configuring BGP on a router can only pertain to one AS, meaning that when I turn on the router BGP process and I instantiate it with this AS, it cannot pertain to any other AS than this. Okay, than the number that I assign under the router BGP. Okay. Number two, when a neighborship comes up between these two routers, doesn't matter if it's iBGP or eBGP, BGP in general creates a TCP connection. It's a TCP neighborship on port 179. Okay, so that's also very important. The third thing is that when you're configuring BGP and your neighborship comes up for the very first time, it exchanges what's called the full BGP update. So under this circumstance, I've configured Acme Edge 1 to announce to the ISP these networks. Okay, so it announces its full set of prefixes that it's been configured to announce out. All right, so the ISP provider here, in this case, is only announcing the default, but it could also be providing us, in a different circumstance, the full routing table. In that particular case, the BGP update, when the neighborship first comes up, is considered full. Now, let's just say, for example, the 188.1677.0/24 goes down. If it goes down, an incremental update from Acme Edge 1 to ISP SHA would be sent, asking him that, or telling him that the 188.1677 has gone down. That's what it means by an incremental update. The other prefixes that were sent do not get affected. Only the prefixes that are having issues, okay, will be sent as incremental updates. All right. So number four, when you announce, or when we announce from Acme Edge 1, these networks, they're going to be tagged with the source or the next hop IP of the neighbor. So under this particular scenario, it just happens to be that we're using the /30 for this neighborship. So if I go on to, if I go under SHA, right? The SHA IP BGP neighbor 200.1.1.2, received routes. Oh, sorry, I don't have this off the. Just the basic. So if you can take a look, the prefixes that are being announced from ACME when they do arrive on Shaw's ISP router, you can see how the next hop is the outbound interface of ACME Edge 1. Okay, so that's very important. All right. The other thing that we need to keep an eye on is if we continue taking a look, this command is very important because you can see that it originated internal, and the updates that are announced, okay, the updates that are announced from ACME to Shaw is it tags its 34987 AS path in it. So from Shaw's perspective, he sees that these prefixes, okay, are reachable via the next hop, and the next hop is basically directly connected. It's a directly connected AS on 34987. Okay. So the fifth thing that I wanted to mention. Now we all know that there are two flavors to BGP. There's there's iBGP and there's eBGP, right? We all know this. Now, with iBGP means that you have an eBGP relationship with another router inside your own autonomous system. Okay? And you could have multiple scenarios, right? Like this. So you could have an iBGP relationship with another router internally, and you could have two of them. The point that we need to understand here is that an iBGP update that is sent to an iBGP peer is never advertised out to another iBGP peer. It stops here. Okay? So the advertisements from ACME Edge 1 downstream to this router will never be propagated to another adjacent router. Okay, so that's a very important point that I'd like to bring out, because when we continue going into this video series, these types of characteristics and these types of things are really key to know. Okay, so I hope you enjoyed this first video, and we'll continue building from this perspective.